Okay, let's just start with this problem that everybody nailed and very quickly. You do x minus 2 into x squared plus x cubed, sorry. 2x squared minus 5x minus 6. And of course, x goes into x cubed, giving you x squared. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. A little minus here and a little plus here to show you what you're really doing when you subtract this from this. And you find that you get 4x squared minus 5x. Divide this into this, you get plus 4x. You get 4x squared minus 8x. You subtract this, you actually add this, and you get 3x minus 6. And x goes into 3x 3 times. 3 times x minus 2 gives you the 3x minus 6. Gives you 0. So that remainder is 0. Thus, x cubed plus 2x squared minus 5x minus 6 equals x minus 2 multiplied by x squared plus 4x plus 3. Okay, makes sense? What about x squared plus 4x plus 3? Does that have any zeros of note? Well, hopefully you know how to factor that. Okay. X plus 1 times x plus 3 gives you x squared plus 4x plus 3. If you didn't know that, well, you know that this has zeros when x equals negative 2 or x squared plus 4x plus 3 equals 0. That's by the multiplication property, the zero property of multiplication. Okay. How do you get the zeros of this? Well, this is easy to solve. X minus 2 plus 2 equals 0 plus 2, x equals 2. That one's solved. And of course, you don't need to jump through a bunch of hoops to solve a solution. You can just see by inspection. But if you can't, you can always do the details, and you can't always do this. Okay? In other words, sometimes you got to do a little work to solve for a penetra like this. We'll see that in a minute. Okay? Or and let's see, we're going to have 16 minus 12. Yeah. Get the wrong number in there. Okay, so we just do the quadratic formula. We get -1, -3, right? Tells us two things. Okay, if it's gonna be 0 and x equals -1, then you gotta have an x plus 1 factor, right? If it's 0 when x is -3, you're gonna have to have an x plus 3. All right. So, all that pretty obvious. What if I find the zeros of x minus 2 times x squared plus 4x plus 7? Well, this equals 0. The zero property multiplication. Either the solutions of this would be the solution of x minus 2 equals 0, which would make the whole thing 0, or x squared plus 4x plus 7 equals 0, which would make the whole thing 0. Well, this is easy to solve. We get x equals 2 just as we did over here. Or x equals -4 plus or minus the square root of -12, I think, over 2. And that would be then -4 over 2 plus or minus, and the square root of -12 would be square root of 4 times the square root of -3 over 2. Now we know that's not a real number. And we know it's not going to give us an x-intercept. You have to have, the x-axis is full of real numbers. So it's on the x-axis. And this is not a real number because square root of a negative is not a real number. There's no real number that you can square and get a negative. Because a negative times a negative is positive. Or positive times positive is positive. Make sure you understand that. So we have this, but I'm going to write this just a little differently. Well, I'll write it another step. This is -2 plus or minus 2 times the square root of 3 times the square root of -1, all divided by 2. And 2 divides the 2, and we get the square root of 3 times the square root of -1. But as you should know, even if you haven't done the assignment in complex zeros, you would have gotten this in your algebra classes, that the square root of -1 we call I. It's an imaginary number. It's the basic imaginary number, and it has a property that I squared equals 1. Now, this is something that people don't have any trouble with when they do the assignment, okay? Just open math will give you the details. You're going to get I squared equals -1. So that if you square the square root of 3i, you get 3 times -1. Okay. Square the square root of 3, you get your 3. Square root of I is -1, so you're going to get 3. Okay. Again, I don't think anybody's going to have any trouble with that. Operating with complex numbers is pretty easy. We'll do a little bit of it. All you got to do is remember that I squared equals -1. All right. So you get 3 zeros. 2, -2 plus the square root of 3 times I, -2 minus the square root of 3 times I. There's only one real zero. There's only one x-intercept. It's a 2, 0. These complex roots can give you wiggles. Okay. In other words, the overall graph of this function would be a cubic function because x times x squared is x cubed. So when you expand this, you get x cubed plus a bunch of stuff. Then you get a plus of -14 and the -2 times 7. Okay. And then you get an x squared and an x term. If you look at it from a long ways away, as we talked about in class last time, long run is like the x cubed function. Wiggles can happen, okay? And they often do. But the wiggles aren't going to take you through the x-axis, except maybe at this point. Okay. And turns out, well, I'm not going to say any more about that. So when you're graphing this, complex zeros are not relevant, but the complex zeros can give you wiggles that happen either above the x-axis or below the x-axis. So the graph could conceivably just kind of look like this, or it could maybe do this. This little wiggle here doesn't give you zeros. The only zero is at 2. But maybe these complex zeros combine to give you a wiggle up here, and maybe not. You don't need to know that, but just for, I'm not going to ask you to analyze the wiggles that you get from the complex zeros. Okay, I'm just saying they're there, but they don't go through the x-axis. And if you don't understand that, just understand this. That's all you really need. Okay. Well, that's pretty much what you need to know to do complex zeros. And it's really, again, people that went ahead and did the assignment did fine with it. Okay. And sometimes there's some mistakes and stuff. One other comment on some of the assignments. I'm going to start not giving you 5 full points on the upload unless I see the details of your solutions. All I see is solutions, and for all I know, you went out on the internet and got them. Okay. Now, you know, if you did that, you probably didn't pass the test. Okay, and I just picked up the tests. And I have to look closely at them. But most of the ones I see look like, you know, they at least passed. I've had a couple of them early in the week, and everybody who took it Monday aced it. Okay. So hopefully some more people did. Because you knew what was going to be on it. I would expect that people did it pretty well. Okay, well, kind of rambling a little bit, but the important thing you need to know now is we're going to have a midterm exam next week. And if you're prepared for the test that you just took, you've got a lot of them. But then, what do we have here? It's going to include quadratic functions, power functions, proportionality. Okay, and I'll get out some sample problems for you. Because of not getting my internet back at home until Tuesday, I haven't been able to get far enough ahead to do that because the whole thing pretty much destroyed my workflow. And I kind of thank my internet provider for that, but at least they got it fixed. And after the hurricane and stuff, I understand how they might have been spread thin. I don't understand why they let my modem run on for several years until it failed before they decided to fix it. That, again, because I've been paying them $10, $12 a month for that modem for years, on the idea that they would service it. But the hurricane maybe gives them an excuse for making me wait 8 more days after we figured out that the modem had crashed. Anyhow, that's neither here nor there. But I am a little bit behind. So this weekend, I hope to catch up and get you some problems. But be sure that you review everything we've done. I'm not going to include the graphs of rational functions, but I will include the graphs of polynomials. And the graphs of rational functions go in there with the rest. I usually like to get that done before we hit November. And we will be done with rational functions next week and get into exponential functions. So again, the only thing I'm saying is go back and review what you've done in this chapter. And by sometime this weekend, I'll get you some sample problems. We'll go over them next week. Because also, I don't have a whole lot of assignments due after Tuesday of next week to give you time to prepare. And I want that done by whatever the drop date is. Okay. Because anybody finds it, you got to find out where you stand on the course before the drop date. And some of you are in excellent shape, and I haven't looked at all the tests, but everybody here has been doing the homework apparently. And I'm expecting it has done adequately well, or hopefully much better on the test. But you need to know that. I would actually accept the test a day or two after the drop date, but that's on you. If you find out after the drop date that you needed to drop, okay. And I hope nobody does. People to succeed here. But as you took the test late. Another thing about drops, if I find that you're really not on track to pass the course, I do have the ability, I don't guarantee I'll do it, but like if you took the test at the very last minute, and I'm not sure you're going to have time to get the results, I would drop you from the course because you can then appeal and I can put you right back in. Okay. And that protects you against getting failing grade. Okay. I don't think anybody here is on the track of doing failing work, but I've looked at all the tests. I just picked them up and have time to even read through them. But I don't guarantee that I'll do that. So, make your own decisions if you do contemplate dropping. You have a better idea after I grade these, and I'll get those results to you probably this afternoon. Because I'll have time to clean this afternoon. All right. Let me pause for a second. Make sure I'm telling you everything you need to know. Very simple rational function. Okay, we're going to come to develop rational functions through several examples. This is a polynomial of degree 1. The numerator is a polynomial of degree 1. And the denominator is a polynomial of degree 1. Okay? If the numerator is 0, it follows that the whole rational function is zero, right? So if the numerator is zero, that means x minus 3 equals 0. So x equals 3. Not much. Okay. If the denominator is 0, well, that means x plus 2 equals 0. So x equals -2. Very simple. Okay. If we do the graph, well, let's another way to write r of x is x minus 3 times the reciprocal of x plus 2. Okay. Now, x close to 2 x minus 3 is close to -1. So r of x is close to -1 over x plus 2. That makes sense? If x is close to 3, or close to 2, since 2 minus 3 is -1, if x is close to 2, x minus 3 is going to be close to -1, right? That makes sense? You look a little confused. Probably haven't seen any reasoning like that. No reason to expect maybe at this point that you should have. Okay, a lot of things you should have seen in your algebra courses that you didn't, but this isn't one of them. That's something that maybe kind of new to you, but it kind of makes sense. Like I'd like to go back and change some of those numbers. Let's go with what we have. Okay, let's say it's close to 2 degrees outside. They got 2 degrees Celsius, which we probably got to this morning. Okay, it's about 1 degree Celsius at my house. But it's 2 degrees Celsius and it's a little colder than it was last night. So it's going to go down 3 more degrees, right? Okay. So if it's 2 degrees and goes down 3 degrees, it's going to be -1, 1 degree below 0. Now, if the temperature is close to 2 degrees and it goes down 3 degrees, doesn't that put us close to that 1 below? Okay, just that simple. Okay, everybody's kind of nodding. Either you're really sleepy or you're agreeing. Okay, so I can say that if x is close enough to 2, we can make x minus 3 as close as we desire to be to x to -1. So that r of x is going to be close to this. And this is what? It's your toolkit reciprocal function, isn't it? But it's reflected through the x-axis. And shifted -2 units in the horizontal direction, or 2 units to the left. Okay. So what we can do now is we can take the graph here. And we can see where x equals 3. And we know that when x equals 3, r of x is 0. Because x equals 3, your numerator is 0, your denominator is 5. 0 divided by 5 is 0, right? It doesn't matter what the denominator is unless it's also 0. You're going to have 0 at that point. Okay. Then at x equals -2, well, that's like we take our toolkit reciprocal graph. And, oh, sorry, toolkit reciprocal graph is like this, and reflect it about the x-axis, which gives us this. That's a multiplication by -1. And then we shift it left 2 units, giving us a graph that looks like this. That picture makes sense. Should, if you understand transformations. If not, go back and review and keep thinking about it until you do, because you're going to need it throughout the course. Okay, you already need it for some of the stuff you got we're just tested on. Okay, so this means that we kind of have something that probably has a tendency to look like this. Here x equals -2. Now, as you get away from x equals -2, x minus 3 is no longer close to -1, right? And that starts messing with the shape of the graph. So you're not going to have exactly this shape at that point, but it'll be kind of like that, at least close to x equals -2. You're going to have an asymptote this way and an asymptote this way, okay? Or you have an odd asymptote where it goes this way and this way. Now, if we want to graph this thing, then what's the y-intercept? Well, the y-intercept that's when y equals r of 0 is -3/2. So we go ahead and just go ahead and draw the line. Y equals -3/2. Okay. And we put the y-intercept there. Okay, so now we've got something that looks like this, something that looks like this, but it has to go through here, and then it has to go through here, and then let's figure out what happens next. Okay, you've got to figure out the long run behavior. But you kind of see, we're kind of wanting to, if I take all that information, I'm saying that the graph might want to look like this, and then like this, it's got to go through the y-axis here, then it goes through here, and then we're not sure what it does here. So maybe it goes into corkscrews or something, but maybe it doesn't. We're not sure about this, so we kind of smudge it out. Okay. That all makes sense so far? Hopefully it does, because that's about as simple as a rational function can get. But there's some complications even with this one. Okay. The other thing we know about this is the long run behavior. It's 1 with a remainder of -5. Without writing out the division, which we already did, this is 1 plus, well, 1 plus, okay, -5 over x plus 2. If x is really big, x plus 2 is really big. And when you divide a really big number into -5, what do you get close to? Divide -5 by the hugest number you can imagine. What number is the result going to be close to? Okay, if you divide -5 by 1,000, what do you get? Okay, well, I wasn't recording when I explained a lot of this, but we understood how we got these 2 points on the graph, the y-intercept and the x-intercept. It came about very quickly. And I think we talked about the fact that this is -1 over x plus 2, which is flip your 1 over x graph and shift it over 2 units to give you something like this white dotted line. Then we ask about the long run behavior. We divide this into this, and we get 1 with a remainder of -5, which means that your quotient could be expressed as 1 plus -5 over the x plus 2. You'd still divide the x plus 2 into the -5, which would give you -5 divided by x plus 2. So that this is another form of R of x. If you put all this over the common denominator, x plus 2, you're going to get what we have over there. Then I said, as x goes to infinity, -5 over x plus 2 goes to 0. That was confusing. I think that's where we stopped and I paused the video. Okay. Ask yourself, if you divide -5 by a really big number, don't you get a number close to 0? Well, if you divide -5 by 1,000, you get -0.005. Divided by a million, you get 0.000005. Okay, negative, but that's close to, it gets closer and closer to zeros, x gets bigger and bigger. That's something you've got to understand, because one of the first things you see in calculus is that sort of reason. Okay, so we really want to be sure we understand numbers well enough to do that, and that's something most people have been challenged by, because you don't really get developed number sets the way the curriculum is designed in secondary schools. Okay, so we got to think about developing that. As an alternative, we can just think of the graph of this thing, or the graph of this thing. You take the reciprocal function, flip it because of negative sign, stretch it by a factor of 5 and pull it over 2 units, and you get this green graph. -5 over x plus 2 would be the white graph here. And then -5 over x plus 2 plus 1 would be this green graph. In the green graph, is the one that we use to do the long run behavior. Now, in the shorter run, it's not exactly like what I've drawn, but that's the best you're going to do in a pre-calculus class. You have to have calculus to reasonably analyze it any further than this. All right. So what we take away is that we look for zeros in the numerator, we look for zeros in the denominator. Zero of the numerator makes the whole thing zero, giving us an x-intercept. A zero of the denominator gives us a vertical asymptote. Okay. Because the zero at x equals -2 came from the denominator, it's going to give us vertical asymptote. All right. So, okay, let's work out another one. There's polynomial. Numerator equals 0. Where is the numerator equal to 0? For what values of x is the numerator equal to 0? And x equals 2 works. Where is the denominator equal to 0? What quotient do you get if you do a long division? And what does all this have to do with the graph? As you get information, start putting it in the graph. Give you a hint. This is 0 when x equals 2. I put the x equals 2 line here, and there's a point of the graph. What's the y-intercept? When's the denominator 0? And what's the quotient you get when you do a long division? Okay? See if you can answer some of those questions. I'll come around and look at what you're doing. But when you get started, I'm going to try to clean board space. Anyway, I guess I can pause the video. And this video would pause when I ask it to. Okay. Everybody's off to a pretty good start here. People are really good with long divisions. Most people do this for sure. Most people didn't get any more zeros than just x equals 2. So we got to talk about how you use the fact that x equals 2 is a 0 to figure out how to get the rest of the zeros. Okay. Y-intercept. Well, most of you have the y-intercept, some of you don't, but the y-intercept is just r of 0. And all the x terms, both numerator and denominator, are going to give you 0. You're going to be left with -6/5. So you got your y-intercept. Okay, so that one is always easy. So make sure you always get it. And then draw it here. Y equals -6/5. And here we've got a point. So there are 2 points on this graph, just like we had on the previous one. And they actually look like they're pretty close to the ones we got on the last exam. Okay. Okay, when's the denominator 0? That means that x is -5. Just solve the equation. Denominator equals 0 means x plus 5 equals 0 because x plus 5 is the denominator. You just write that down and solve for x. Okay. Now, if the denominator is 0, that's going to tend to give you a vertical asymptote. Well, we draw the line x equals -5. Then I kind of recommend making that line a little more solid. Maybe light, but solid. So you know that's going to be an asymptote, and you don't think that this is going to be an asymptote. Of course, you got a point marked on here. That means you're just marking the x equals 2 line so you can locate the asymptote, the 0. Okay, so most of this comes out pretty easy. But what happens near this asymptote? And are there other x-intercepts? Because this is a cubic equation. You know that a cubic equation could have up to 3 zeros, 3 real zeros, which will give you 3 intercepts. Another thing you know about a cubic equation that you might not have known is that, like any polynomial, this thing factors into linear and irreducible quadratic factors. Okay, we're going to see how that works. All right, so long division, well, we can go ahead and dispose of that. You get x plus 5 into x cubed plus 2x squared minus 5x minus 6. And you don't always have to do the long division to graph the thing, but they can often be helpful. So there's one thing that you want to take away from the long division. Let me go ahead and do this. Everybody's really good at it, so I'm not going to explain. Just tell me if I'm making a mistake, scream or something. The way I work, there'd be a lot of screaming, so maybe we better not do that. That's 10x plus 15 minus. So there's the quotient. Now, really, the thing that we understand about the quotient is that if x gets really big, then this part gets really big, right? Maybe positive, maybe negative, it gets really big. And this gets really small because as x gets big, your denominator gets bigger and bigger, and your numerator is going to be a smaller and smaller part of that denominator. So this approaches 0. Okay. So down here we can say, as x approaches infinity, r of x, which does equal x squared minus 3x plus 10 minus 56 over x plus 5, approaches x squared. Now, open math gave you plenty of discussion about how x squared is going to be much bigger than 3x or 10. If x is 1,000, x squared is 1,000,000. Negative 3x is only negative 3,000. You take 3,000 away from 1,000,000, you get 997,000, okay, which is close to 1,000,000. These numbers here end up not amounting to a hill of beans when x gets big enough. X squared is more powerful. That's why we call it a power function, okay? The highest power tells you how R of x behaves. So that the long run behavior is just the behavior of a x squared function, okay? Which means then long run goes up like this here, goes up like this here. That makes sense? You don't have to do long division to see that, of course. Open math tells you if the degree of the numerator is at least 2 more than the degree of the denominator, then it's either going to be up on both sides, down on both sides, or up on one side, down on the other. And you have the rules. But if you do the division, you can see a little bit more and understand what function it is that this is embedded in. What we're looking at here is the wiggles, and in this case, the asymptotes, the wiggles and the spikes. Okay, you got to get spikes here. You got to get maybe wiggles in here somewhere. Okay, well, we need more zeros. Okay. Numerator has 3 zeros. Which can yield up 3x intercepts. Now, some of the zeros might be complex. They don't lead to x intercepts. Only the real zeros lead to x intercepts. You got one real zero, that's x equals 2. Okay. Well, divide x minus 2 into x cubed. Oh, here, x cubed plus 2x squared minus 5x minus 6. And I believe we get x squared plus 4x plus 3. So power of x can be written this way, right? Uh, not R of x, it's the numerator. So your numerator, that's NUM, is this, which equals x minus 2 times x plus 3 times x plus 1. So you can immediately see that you have 3 zeros. So 0 at x equals 1. 0 at x equals -3. So we've got to go through the x-axis here, here, and here. Got to go through the y-axis here. We've got to have vertical asymptote here. Well, that means your vertical asymptote over here has to be above the x-axis because the function starts out from way high and it comes down and then makes a vertical asymptote here. So what's the graph look like? Well, it looks something like this. It comes down here, at some point it turns around and goes up. Okay, you know it has to do this because it starts high and it can't go through the x-axis because the only place it can go through the x-axis is where the numerator is 0. Then it has to switch on the other side of this asymptote. Oh man, we've got trouble. Yeah, there's a problem with this. Something's wrong. Hang on. Okay, now what was wrong, and I'll point it out, and I really made the mistake, just being careless. The asymptote has to flip down here because it's like a 1 over x plus 5, okay? And you then come up through this point and you can't get back to this one. Because once I come up through this point, I can't turn around and go through the x-axis until I get to one of the other zeros. And I can't come around here and loop and come back because you wouldn't have a function. You'd be failing the vertical line test. Well, it was simply that I looked at x plus 1 and wrote x equals 1 as a 0, and it's -1. Okay? So if that happens to you, you can't get there from where you are. You fix it. First, you make sure you got your zeros right. And to my limited credit, that's the first thing I looked at because I knew I needed a 0 over here. Okay? And it didn't take me too long to find it. But okay, here's x equals -1. And right here is your 0. Now we can come up from the asymptote through here, turn around and go through here, come down through here, and then come back up through here. There's our graph. So the overall graph looks like x squared, except it's got some wiggles. So it wiggles a little bit in here, and it's got a spike. So it actually has to turn around here and go up and come down from here and all that stuff. Okay, so you got a wiggle and a spike. There's a wiggle and there's a spike. That makes sense? Spikes come from zeros to the denominator. Zeros to the numerator tell you a lot about wiggles, but they don't tell you everything there is to know. There can be wiggles above or below the numerator that are going to be, or above or below the x-axis. That don't go through the x-axis. And you don't have in pre-calculus a way to determine that. You go to a graphing calculator, but that's worthless. Doesn't tell you anything. So in calculus, it turns out to be pretty easy to find the wiggles. Probably easier than anything we've done here once you understand a few simple rules, okay? So you have that to look forward to if you're going to take calculus. It's one of the easier things in calculus. Right here. Okay, so we've done 2 examples so far of rational functions. These are the questions you always ask yourself. And the answers tell you all the information you need to get a decent approximation of the graph. As I just pointed out, there are going to be things about the graph that you're not going to be able to do accurately. just because you need more knowledge of calculus. And so forth, but you can at least get the overall behavior. Now, if you actually graph this thing with a graphing calculator, in here, it's gonna probably look fairly similar to what I did out here and with the asymptotes and stuff. Yeah, probably similar here. Here, I don't know how high or low this thing's gonna be. I can figure it out in about a minute. Just take a derivative, so it equals 0, it'll be quadratic. But, as I say, that's one of the easier things to do in calculus, okay? Always ask these questions, write these questions down. Write down what it is you have to do. So let's just look at one more example. We've only got about 4 minutes. We don't really have time to do another thing. So rather than confusing you with another example that I can't fully explain, we'll just stop there for today. But remember that you want to get a head start on preparing for the midterm exam. Okay, which is going to count twice as much as the test you just took. Unless the test you just took is really helpful, in which case it'll count as much as a midterm. Okay. So, but the midterm will be heavily counted, and then final exam will be.